Welcome back to STEMLens. In today's video, we shall be talking about matter from Lamlad chemistry. In the last video, we talked about the concept of living things from college biology, that is the Idodo Ume biology. And today we'll be talking about matter. So let's dive into it. We have classification of matter. Matter is anything that has mass and occupies space, that is everything seen or unseen. Now, before we dive deeper, let us look at the difference between mass and weight. Now, when we talk about mass, you are talking about the stuff, an object, a substance is being made of. But when you talk about weight, you are talking about the force acting on that stuff, that substance, due to the pressure of gravity. That's acceleration due to gravity. Now, another keynote difference you should take note of is that weight changes with location. Meanwhile, mass does not change with location. Now, to get the weight of an object or to get the weight of a substance, it is just the mass times the gravitational force in that area. So now, matter is anything that has mass, not weight. Mass and weight are different. Anything that has mass and occupies space. Now it says, on a broad basis, matter can be subdivided into two general categories, which is the pure or distinct substances and impure substances, which are the mixtures. Now, the pure or distinct substances consist of the element and the compound, while the impure substances generally are also known as what? Mixtures. So, pure substances are distinct substances having the following general properties. Number one, all the parts are the same throughout, that is, they are homogeneous. The composition is definite. They cannot be easily separated or broken down into simpler substances by physical means. Separation by physical method is not easy, and they have a unique set of physical properties, for example boiling point, melting point, density, physical state, spectroscopic properties, etc. So now, in pure substances such as elements and compound, the composition is definite and it is the same throughout. Now, they cannot be easily broken or separated down into simpler substances by physical means. I used to say separation by physical method is what? Not easy. And they also have, lastly, they also have a unique set of physical properties. Give examples: boiling point, melting point. Now, these physical properties are unique as said, and in fact they are being used as the criteria for determining the purity level of substances. Just as the name implies, pure substances, they have a high level of purity. That's why they are being called pure. Impure substances, they have impurities in them, they have contaminants in them. That's why they are being called impure substances. For example, the mixtures. Now it says pure solid substances have sharp melting point or very narrow melting range. We are still going to talk about melting point and boiling point under this concept. Let's just understand what this place is saying. Example, a reasonably pure benzoic acid sample has a melting point 122 degrees Celsius or a melting range 120 degrees Celsius to 122 degrees Celsius. However, impurities, that is contaminants, cause a depression in melting point and the widening of the melting range of solid substances. Example, an impure substance or an impure sample of benzoic acid has a melting range 110 degrees Celsius to 118 degrees Celsius. For liquids, you can see how it dropped from a melting range, a sharp melting range and melting point of 122 degrees Celsius to a melting range of 120 degrees Celsius to 122 degrees Celsius. Impurities opened the melting range down to 110 degrees Celsius to 118 degrees Celsius. That is what impurities can do. For liquids, the criterion for determining the purity level of sample is the boiling point or relative density. Now, a reasonably pure liquid has a constant boiling point or a low boiling range. Example, 99 degrees Celsius or 98 degrees Celsius to 100 degrees Celsius for distilled water. Impurities, however, cause an elevation of the boiling point and the widening of the melting range of a hitherto pure liquid. Example, 99 degrees Celsius to 105 degrees Celsius for an impure water sample. I said earlier, pure substances are either what? Element or compound. Now let us talk about the state of matter and phase changes. Chemists usually describe substances as matter. Each form of matter is made up of aggregates of small particles called molecules. Molecules consist of one or more tiny particles called atoms. A molecule may be monoatomic, for example helium, neon, argon, or diatomic, for example hydrogen, oxygen, nitrogen, chlorine, or polyatomic, for example ozone, phosphorus, sulfur, and others. Hence, we have the chain to be atoms to molecules to matter. Now, matter exists in three phases commonly referred to as the state of matter. These are the gas, liquid, and solid. Now, the particles of a gas or the molecules of a gas are very far apart and are held together by weak attractive forces. Those of a liquid are much more closely held together by stronger attractive forces, and those of a solid are most closely held together by very strong attractive forces. Now, the degree of entropy in gases is much. When you talk about entropy, you're talking about the degree of disorderliness. So gases have a high degree of disorderliness because of the weak attractive force between their molecules. So they tend to move far apart from each other, they tend to collide with each other in their movement, and that is why we have gases, they take the shape of the container, a lot of other characteristics which we are still going to talk about later on. For liquid, they are held together so that they follow each other, they lag, they follow each other. If water go here, see the rest following it. But for solid, they are very, very closely, tightly packed together. Right? So we have a diagrammatic illustration here. You can see the gases, how the molecules are far apart. You can see the liquid, they are clustering somehow. But you can see the solid just tightly packed. Alright? It says some typical examples of a gas are helium, oxygen, carbon dioxide. Examples of liquid are what? At room temperature, methylated spirit, and mercury. Mercury is actually a metal, right, but it is a liquid. Examples of a solid are copper iodine crystals and sodium chloride crystals. That's your salt crystals. Now, under suitable conditions, the three states of matter are interconvertible as shown below. That's in this figure 1.2 phase transfer process. We can see, okay, it is a graph of pressure against temperature. A graph of pressure against temperature. We can see solid by our left, we can see liquid above, we can see gas below. Then we can see a point here, a point 0. We have A, B, C. We can see a point 0. That's the point where A, B, and C meet. That point is known as a triple point. It's a point O is known as the triple point. That is the pressure and temperature at which the three phases of a pure substance coexist with each other, with one another. For pure water, the triple point is 0.01 degrees Celsius and 4.5 millimeter mercury. Please take note of this point. I will probably come back to it later on. 0.01 degrees Celsius and 4.5 millimeter mercury. Alright, so now the phase that's at which solid, gas, liquid coexist is the word triple point. Let's move on. We have the phase transfer processes are freezing, melting, boiling, condensation, and sublimation. We also have deposition. Right, I will chip it in when it's necessary. Okay, for solid to liquid we have melting. For liquid to solid we have freezing. That's to convert a solid to liquid. The solid has to undergo what? Melting process to be converted to liquid. Liquid have to undergo the freezing process to be converted to solid. Liquid have to undergo the boiling process to be converted to vapor. Vapor have to undergo the condensation process to be converted to liquid, and solids, the sublimation, to be converted to what? Vapor. Now the relationship existing among the phase transfer process is shown in the phase transfer triangle. Alright, so they give us a triangle, a diagrammatic illustration which will be more better to anchor in your brains. Alright, so we have, let's take from solid to vapor to liquid. So from solid to vapor we have sublimation. From vapor to liquid we have condensation. From liquid to solid we have freezing. Now let's go in anti-clockwise direction. From solid to liquid we have melting. From liquid to vapor we have condensation. From vapor to solid we have condensation as well, but we could also have deposition. Alright, take note, deposition. It says here, when a solid is heated, it normally melts and changes to a liquid, which on heating changes to the corresponding vapor. Solid, liquid, vapor. The randomness of the particles increase. That's what I spoke about earlier. The randomness of the particles increases. That's the entropy increases. That's the entropy increases. That's why solid have the least entropy, liquid have a moderate entropy, and vapor have the highest entropy. Alright, from solid state to liquid state to gaseous state, the randomness of the particles increases. Figure 1.4 shows the arrangement of the constituent particles as phase transfer occurs. So you can see from this figure 1.1, which is the heating profile of a solid, you can see that this solid still coexisted with liquid before finally going into the liquid phase. The liquid also coexisted with vapor before finally going into the vapor phase. So that's just how it is. The phase changes occurring during the heating of a solid as shown on the heating curve, a temperature time graph of the solid. Okay, figure 1.5, let's look at it. Okay, it is a graph of temperature against time, the heating curve of a solid. So you can see the solid, when it got to the melting point, it coexisted with liquid. Now it's finally everything changed to liquid, and then when it got to the boiling point, the liquid started turning to vapor. That means it was coexisting with vapor, and then as it overpowered the boiling point, it turned to vapor. Alright, so we have a note here still on this curve. It says the temperature at which the vibration of the particles of a solid becomes so great such that the mutual attractive forces are overcome and the particles break free from the fixed lattice position and slide over one another in a liquid state is called the melting point. At this point, the solid and the liquid phases are in equilibrium. Even though heat is continuously supplied to the solid, the temperature is constant at the time of melting. Generally, the heat absorbed by a substance in changing from one phase to another is called the latent heat. Now when you hear latent, you know it's hidden. The amount of heat absorbed which caused the change of phase to occur at the melting point is called the heat of fusion. The magnitude of this heat energy depends on the nature of the solid and the strength of the attractive forces between particles. Now what this is trying to tell us is first told us that the temperature at which the vibration of the particles of a solid becomes so great. Now that's the melting point. It is a phenomenon, right? So this melting point, you can see m.pt, that's the melting point. It is at that temperature, the melting point temperature, that the vibration of the particles of solid becomes so great that the forces holding the molecules tightly are being broken. Those forces are being overcome. So the particles break free from their lattice positions. Right, they begin to slide over one another as in liquid. So as at that state, the liquid is coexisting with the solid till all the solid turns to liquid, and then we look at the boiling point. Now about this latent heat of fusion. Latent heat of fusion says the amount of heat absorbed which caused the change of phase to occur at the melting point is the latent heat of fusion. Now they all have latent heat. Is the heat of fusion. They all have latent heat. But now they need to absorb more heat. Like for example, an ice. When an ice wants to change to a liquid, that's to water, its heat has to be absorbed by the ice to break the point and to pass the melting point. That's to get to the melting point. So once it gets to the melting point, the ice begins to turn to liquid water. That heat absorbed by the ice during the process of turning to liquid water is the heat of fusion, right? Now it says when heated, some solid however vaporize directly without passing through the liquid phase. On cooling, the vapor also turns to the solid phase. This phenomenon is known as sublimation, right? We spoke about it. If you can see by your left, the phase transfer triangle, solid to vapor is what? By sublimation. Solids having unusually high vapor pressure exhibit this property. Example of such solid include iodine crystals, ammonium chloride crystals, naphthalene, camphor, and dry ice. Similarly, boiling point is the temperature at which the liquid and vapor phases are in equilibrium. The boiling point of a liquid depends on the prevailing external atmospheric pressure. The lower the external pressure, the lower the boiling point of a liquid, and vice versa. The amount of heat absorbed that causes the change of phase, that is liquid to vapor, to occur at the boiling point is the heat of vaporization. At the melting point, we have the heat of fusion. At the boiling point, we have the heat of vaporization. So now boiling point is actually is related to the external environment. For example, at higher altitude, you will notice that water would boil faster, liquids will boil faster. right? Because boiling point is just the temperature at which the liquid and vapor phases are in equilibrium. Okay, that's that for that. The boiling point depends on the external or atmospheric pressure. It depends on the atmospheric pressure is low, water is likely to boil faster. Alright, now we have properties of matter. Properties tells us what a substance is or what a substance can do. The properties of matter are classified as either physical or chemical. Now, physical properties tells us everything about what a substance is when no change is occurring to its constituents. Such properties are observed with our senses or instruments or pieces of apparatus. Examples are state of matter, color, odor, taste, texture, hardness, solubility in water, melting point, boiling point, density, viscosity, and spectroscopic patterns, IR, UV, NMR. While chemical properties are those properties that tells us about what a substance can do as regards to whether or not the substance reacts with other substances. Examples are flammability, rusting of iron, precipitation, decomposition of water by an electric current. So now chemical properties has to do with reactions. Let me just put it that way. But physical properties, you can just see them, you can observe them. For example, when you are boiling water and water begins to turn to vapor, you know that it's turning to vapor. It's something you can actually observe. But chemical properties, you may have to bring in one or two tests to be sure, alright, that there has been a change in the chemical property. Alright, that takes us to changes of matter. The changes that matter undergoes are associated with properties. The changes are therefore categorized into physical and chemical. A physical change is one that alters the physical properties of matter, particularly the form and state. In many cases, this change is easily reversible. Examples are changes of state such as boiling, freezing, sublimation, magnetization of metals, breaking glass, and cutting wood. A chemical change is one in which new kind of matter is formed. It is always accompanied by energy changes, that is, evolution or absorption of energy in form of heat or light or both. This process is not easily reversible. Examples are combustion, roasting of iron, precipitation, and souring of milk. The silent differences between physical changes and chemical changes are given in table 1.1. Alright, before we look at this table, right from the physical properties, if there is a change in the physical property, there is a change in matter. So depending on which physical property undergoes a change, like if there's a change in a physical property, it is a physical change. There's a change in a chemical property, it is a chemical change. For example, physical changes now, when you freeze your water, it turns to ice. That's just a physical change, don't forget. That's a physical change. When you boil your water, it turns to vapor. Boiling point is a physical property. Now, when there is a change, when it boils, that is a what? Physical change. But now, in terms of rusting of iron, combustion, for example, when you burn, another thing to notice is that in physical changes, new products are not always formed, but in chemical changes, new products are always formed. For example, when you burn wood to ashes, you cannot reverse that process. But when you freeze a water to ice, you can actually, upon heating, the ice can still turn back to water. But when you burn wood, or you burn your textbooks, or you burn your phones, or whatever you burn, combustion in general, when you burn it, you cannot bring it back to the former state. No. That burning will even release energy. That's what it says. It says it is always accompanied by energy changes. So now let us look at the differences they gave us. It said physical changes are easily reversible, while chemical changes are not easily reversible. Physical changes lead to the production of no new kind of matter, while chemical changes lead to the production of new kind of matter. That's production of new kinds of matter. Physical changes involves no change in mass. No. Now when you freeze your water, it is the same amount of mass. When you unfreeze it, it is still the same. But now when you burn your books, you may burn a book in a whole room. Even human beings, they may burn a dead person and the ashes will just be so little. You can see that there will be a large observable change in mass of the burnt material or the burnt matter. Now physical changes require little energy, while chemical changes require a considerable amount of energy. So that's all about physical and chemical change. In the next video, we shall be talking about element, compound, mixture. So thank you for joining us in today's video. See you next time. STEMLens.